So I've got a Rankine cycle with properties given here, and I have isentropic efficiencies on the turbine and the pump. So I started my table for setting my states. So again, state 1 given in the problem. So I'm going to go ahead and look up H1 and S1. And then once I know S1, I'm going to be able to find S2. Okay? Because across the turbine is isentropic. So let's go ahead and go look those up. So it's 16 megapascals and 560 degrees Celsius. You can see that my H is 3465.4 and my S is 6.5132. So I'll go ahead and jot those guys down. So that's going to be 3465.4, and then S is going to be 6.5132. Again, first thing I need to do is find the optimal performance of my turbine. So that's the isentropic performance. So S2, I should say S2S equals 6.5132. Then using that pressure and that entropy, I can find the best case scenario for my enthalpy. Okay, this would be my isentropic enthalpy. So I'll go to 8 kilopascals, which is 0.08 bars. Okay, and you see that my value of 6.5 is in between these two values for entropy. So I do a interpolation between these two values to figure out what my H is. And my ideal enthalpy is 2037. Okay, so that's the best case scenario. Of course, now I have my turbine efficiency that I need to include, which is going to be H1 minus H2 all over H1 minus H2S. And from this, again, knowing that this is 85%, I can, from that, calculate H2. Why do I have a 4 there? H2. And plugging in my values for H1, H2S, my efficiency, I get 2251.3 when I do that calculation. So this is, again, the actual performance. This is the isentropic or best case performance. Okay. State 3, I'm going to be able to look up. Okay, and I can go ahead and look up H3. And then for the pump, what I'm going to do is I'm going to use VDP equals delta H. So I'm going to go ahead and look up my volume too, because I'll take that volume times the change in pressure and set that equal to delta H, because I can find the work of the pump each of those two ways. Okay, that will actually get me H4S. We'll get to that in a second, but I'm going to go ahead and look up H3 and V3. This is for saturation at 0.8 bars. So my volume is right here. Okay, 0.00100084, and then my enthalpy is 173.88. Okay, so again, my volume was 0.00100084, and my enthalpy was 173.88. Okay, now in order to find H4S, I'm going to, again, figure out the isentropic case. That would be, again, for a pump, my isentropic is V times the change in pressure. That's for a steady state, isentropic, incompressible flow sort of deal like I have with the pump, which also equals H4S minus H3. And again, from this, I can find H4S, which is my best case scenario. Okay? And from that calculation, I can find H4S is 190.01. Of course, that's not the real answer. That's the best case answer. I'm at 85% of that. So I'm going to use my pump efficiency equation, which is going to be H4S minus H3 all over the actual H4 minus H3, right? Idealized over the actual. From this, I can go ahead and calculate H4 because, again, my pump efficiency is at 85%. Okay, so I can find my H4 through that calculation, which is 192.86. And there I have set all of my states. And then once I get that, I can go ahead and find my thermal efficiency. So again, for these, I use constant entropy and then isentropic efficiency. And this one, I use what I know about an isentropic pump to find the ideal, and then I use the isentropic efficiency. Okay, so my thermal efficiency, which is what I'm looking for, is again the work of the cycle over Qn, which is going to be the work of the turbine, which will be H1 minus H2, minus the work of the pump, which is going to be H4 minus H3, all over Qn, which is H1 minus H4. So plugging in all those values for H, I can find an isentropic efficiency, a thermal efficiency of 36.5%.